So hello everyone, this is lecture 48 for the mathematical physics. In the last lecture we have seen some definite integrals of fx dx type and limit was minus infinity to infinity. Okay, now we will see some more kind of integrals like this. Means now you have exponential in the integral. So integrals with complex exponentials. So now you need to solve this definite integral using complex integrals. So how we can do that? So first they should satisfy some conditions, only then you can apply the formula. I will tell you. So first fz, if you take in place of x equal to z, then fz should be analytic in upper half plane. So this is minus infinity to infinity, so you will take this x-axis. So this is x-axis, so there will be this upper half plane or lower half plane, so it should be analytic. fz should be analytic in the abject plane in all points except some points. Okay, so there can be some points where it is non-analytic. So this argument will be 0 to pi except a finite number of poles, otherwise it should be analytic. No singularity on real axis, so there should be no singular point at the x-axis, only then you can apply, and this condition should satisfy. So what is this condition? Means this, if this is your formula, then fz exponential I az, then this fz dz means, sorry, this fz and limit z tends to infinity should came out to be 0. When this condition is satisfied, then you can apply this condition. This is Jordan's lemma. Means when r tends to infinity and fz equal to 0, then for all z equal to r exponential I theta, where theta is 0 to pi, so for all these z, this should satisfy this condition. Then you will say that this contour integral means up to this outer one, so this cr integral fz exponential I az dz will be 0. So this will be 0. Now what is the benefit of this thing to us? Means now if we need to find the integral, then we will take in place of x z, then we will solve for this closed contour, and this closed contour will be sum of this x-axis plus this contour. So this will be 0. So whatever you will get from fz will be equal to this x-axis, and that will be equal to the real this definite integral. So that's how it is very helpful. Let's see one example, it will be more clear then. I equal to 0 to infinity cos x divided by 1 plus x square dx. So first we have to change this limit in the form of this. So we'll change it minus infinity, because this is a even function, so we can write minus infinity to infinity 1 upon 2. Okay, now see, this is not in the form of exponential. Let assume there is function this exponential I z divided by 1 plus z square. In place of x we place z, and we assume some exponential I z, because this will give you cos z plus I sin z. So in the last, when you solve this integral and you will get whatever value for this, then you can compare that with this. Means you can separate the real and the imaginary part, and real part will give you integral this. So just forget this, see this only from here. Let this is your fz dz, and now it can be written in this form. Means this is closed contour and this is minus infinity to infinity and the closed contour. So it will be for the x-axis, it will be minus infinity to infinity, and this will be real function exponential ix. In place of z you will write x plus this closed contour this one. Now that should be 0, because if this is your fz 1 plus z square, then fz at z tends to infinity is 0, because 1 upon infinity will be 0. So that's why it will satisfy this condition, Jordan's lemma. So we will say that this should be equal to 0. Now if this is equal to 0, so this will be equal to this. Now this is a complex integral, so you know how to solve this. Just find the residue and multiply 2 pi iota, so that will give you this integral, and this will be equal to this. Now when you expand this, you will get real term and the imaginary terms. So real term will give you this integral, and imaginary term will give you anything else. So you just need the real integral. So that's how you can calculate this value from this kind of thing. So whenever you will get cos x or sin x here, so you will use this kind of integral, and that will give you these results. So let's see how this will give us this result. So we assume this. Now this will be 0. So this integral will be equal to this. So we need to solve this integral. So first find the singular points for this. You know how to solve this. 1 plus z equal to 0. So z will be plus minus iota. Now in this contour, only plus iota is lying inside. So we need to find residue for plus iota only. So z equal to 1 iota. The residue will be limit z tends to iota, z minus iota, and this is your fz. So exponential I z divided by z minus iota, z plus iota. This will cancel out, and iota will give you 2 iota here. It will be, and z here, I square will give you minus 1. So exponential minus 1 divided by 2 iota. And this will be 1 upon 2 exponential iota. So this is your residue at z equal to iota. So integral will be 2 pi iota multiplied residue is this. So this is your integral pi by e. So this integral is equal to this pi by exponential. Now see, this is equal to this. You can expand this in the this is nothing but exponential I theta. So this is cos theta plus I sin theta. So it is cos x plus I sin x, and you can separate this denominator. So cos x divided by 1 plus x square and I sin x divided by 1 plus x square. So this is in the real form. So there is 0 iota. So this sin x will be equal to 0. Now comparing on, you will get cos x by 1 plus x square equal to pi by exponential. So that's how you can calculate this integral. Now we need this one. So this is nothing but this is even function. So it is 0 to infinity and 2. So that's how you get 2 will go this side and pi by 2 exponential. So this will be your integral. So that's how you can solve this integral using this. So whenever you will get cos or sine this kind of function and exponential in it, you will use this. You will assume this kind of function. Wherever x it is z, and in the place of cos sine you will write exponential iz. Just like means from here what result we can also derive, means from here this sine part will be 0 because there is 0 iota. So this will we will get on comparing this is equal to 0. So if it here it will be sin x, then it will be 0, and you can see this result also. This is odd function, or then it will be definitely it should be 0 because for the f minus x equal to minus fx. So this is your odd function, so this should be 0, and from here also we are getting this equal to 0. So that's why this proves the result. Now there is a general formula. If it is given in the form of 0 to infinity cos mx divided by a square plus x square, where m is greater than equal to 0, then this integral will be directly pi by 2a exponential minus ma. Okay, now you can see this result. Here it is m is 1 here and a is 1 here, m is 1 and a is 1. So just substitute in place of this. So m is 1, a is 1, it is exponential minus 1, and here so pi by 2 exponential. So you will get the same result. So just remember this formula. For sine also we have the general formula, x sin mx x square plus a square. If you have this kind of integral, then result will be pi by 2 exponential minus ma, where m should be greater than equal to 0. So that's how you can write the integral directly. Now let's take a different kind of integral. So this is 0 to infinity 1 upon 1 plus x cube dx. Now we need to solve this. So if this function was even, then it will be very easy to solve, because we can put this minus infinity to infinity, then we can solve the half. It means we can take the half plane of the semicircular plane. But now it is not even, and it is not even odd. So how we can solve this? So we need to first make a contour, closed contour, only then we can solve this, because we need to take this closed contour 1 upon 1 plus z cube dz. So in place of x we write z. Now how can we make this a closed contour in the real, if we want to imagine this, how this closed contour will look like? So see, for this x, this is on x, so 0 to infinity this should be this line. If r is tending to infinity, then 0 to infinity will go like this. So we need to find this integral. So we need to find this integral. Okay, limit is 0 to infinity. Now we will take a closed contour. If it was even, then we take this to this side, but it is not even. So what we will do, we will find another line which will make it closed contour, and that line is related to this a line also. Okay, means there is some relation between this integral and this integral, so we can find this integral. Okay, so we need to find that relation, and then we can make this closed contour. So how can we find that relation? So in place of z we will write r exponential I theta. So z equal to r exponential I theta, because this is the same in whole the complex plane, z equal to r exponential I theta. Now for this one, theta is 0, so z will be r for this. So in place of the integral when we write, so we will write just in place of x we will write r. Then we will find that some another line where this z cube should be equal to r cube. Okay, so we need to find that kind of integral which will relate to this integral. Okay, only that line is required here. Otherwise we can take another line, but we need only that line which is relatable to this integral. Means the integral along that line should be related to this integral. So we need to find that line. So we need to put a condition here that z cube equal to r cube. So when you put z cube equal to r cube, so it will give you exponential I 3 theta. So z cube will be equal to r cube, and this exponential I 3 theta will be 1. So that's only possible when 3 theta should be equal to 2 pi. So theta should be 2 pi by 3. So that's how we can find the second line. It means this theta should be 2 pi by 3. So we just find it, this theta is equal to 2 pi by 3. So for this one, this z equal to r exponential I 2 pi by 3. So remember this. Now we will write this closed integral. How? This is equal to sum of this integral plus this integral plus this integral, and this is a, you know, if you write z fz means then z fz at z tends to infinity will give you 0 here. So this condition is satisfied, means for this contour, only this contour, the integral will be 0. So now see, you can expand this integral into 3 parts, that is 1 is this, 2 is this, and 3 is this. So this will be equal to this integral plus this integral plus this integral, and this integral is 0, and this is equal to 1 upon 1 plus r cube. So you can write this integral like this: 1 upon 1 plus z cube dz is nothing but 0 to infinity, first because r is tending to infinity, 1 upon 1 plus r cube because z equal to r for this line, this one line. Now this second is, this closed contour is 0 because z fz equal to 0 for r tends to infinity. Now this third one is infinity to 0, so this is the limit. So here z cube equal to r cube, and z equal to what? Z equal to r exponential I 2 pi by 3. So dz will be equal to dr exponential I 2 pi by 3 and 1 plus r cube. So for this third one you will get this thing. Now see, you need to find this because this is on the real axis and this is x, we know. So we need to find this integral. So for this integral, what we do means, for this whole value we need to find, then we need to calculate this integral, and we know how to calculate the complex integral. We need to find the residue points, and 2 pi iota multiplied sum of residue will give you this integral. So for that, first find the singular points for this 1 plus z cube. So what will be the singular points? So 1 plus z cube equal to 0, so z will be cube root of minus 1. So first root will be this 1 plus root 3 by 2, means 1 plus root 3 iota divided by 2, and this can retain in this form exponential I pi by 3, and second root will be minus 1, so it can retain as exponential I pi. Now z3 will be 1 upon 2 minus root 3 by 2 iota, and this can retain as exponential 5 by 3 iota. So these are your 3 roots, okay, means 3 singular points. Now see which one is lying inside the contour. This is your contour. Now you see z2 is minus 1, so it will lying somewhere here, so it is not inside. And z3 is x 1 upon 2 and y is minus 3 by 2, so it will lying somewhere here, so it is also not in contour. But this z1 1 plus root 3 iota divided by 2 is lying somewhere inside first quadrant, so this will be inside this contour. So we need to find residue only for this point, and that will give us the integral value. So z1 is nothing but 1 plus root 3 iota by 2 or exponential I pi by 3. So let's find the residue for this one. So how you find the residue? Limit z tends to z1. For z1 it is inside, so z minus z1, and fz is 1 upon 1 plus z cube, so you will get this form. Now for z1, this will be 0 and this will be 0, so this is a 0 by 0 form, so you will use L'Hospital rule. So this will be 1 upon, and this derivative of this will give you 3z square. Now just put the limit z1 here. So z1 is nothing but exponential I pi by 3, so this will give you residue 1 upon 3 exponential 1 iota 2 pi by 3. So 2 pi iota multiply this will give you this value, integral of this, and you need to find this. Now see, this is the constant, and this whole term, if you write minus here, then it will be 0 to infinity again. So this is minus I. If we call this I, then this will be I exponential I 2 pi by 3. Now this will be your form, and we just solve this integral. This is 2 pi iota multiply residue, and we already find the residue. Now you will take iota common from here, you will get 1 minus exponential I 2 pi by 3, and iota, this I will be equal to this divided by this 1 minus exponential I 2 pi by 3, and you already find this residue, that is equal to this 1 upon 3 exponential I 2 pi by 3. Now we will substitute in place of this value. From here you can find this I, that will be equal to minus 2 pi iota divided by 3, means this is equal to this. Now I will be equal to this, will go to the denominator, so it will be like this kind. Now see, this 2 iota will also go in the denominator, so you will get this form. Now this is nothing but this is sine pi by 3, so you can just remove this, and you can write I equal to pi upon 3 sine pi by 3. Now sine 60 is nothing but root 3 by 2, so this will be your integral value. So that's how you can solve this kind of functions, or you can find this kind of definite integral using this. So I hope you get this. If you not, then please you can ask me in the comment section wherever you are having doubts. So let's see one more kind of integral. Now our pole or the singular point is lying on the x-axis. Here it is x naught. Then how we can solve this kind of integral? Okay, so let's see. What is Cauchy's principal value? The Cauchy principal value is you need to find this integral except at this point. Then that is the Cauchy's principal value, we call it. Okay, so and here we will see only that function which have a simple pole. Okay, only for that we will solve this. So here fz has a simple pole on the x-axis itself. Now this fz dz, if this is your contour, if this is your point where it is non-analytic or singular, then we make a smaller curve here. Okay, contour here, and we make this kind of contour. Okay, and leaving this point. So this is your closed contour C, and this is the contour. This means this is taking means except this point, this is at all these points. So this will be your integral. This is equal to minus r to minus delta, means we take this delta and this delta tending to 0, very small. So this minus r to minus delta, then this C1, and then it will go from delta to r and then r to minus r. So means this is, we call this as C2 and this is C1. So you can write this complete integral in this form for this closed contour for the minus r to minus delta fx dx, because here in this axis z is equal to x, that's why I have written this. And then this is your, we call this I over. Okay, I over. So this is nothing but fz dz, and again we have delta to r fx dx, because it is depending on the x-axis only. Now for the C2 we'll write the C2 fz dz. Just forget this yet. Okay, we have this 4 parts for this closed contour, just remember this. Now this 4 parts will be equal to whatever the value of this integral. So you can solve this integral using the same methods, means 2 pi iota multiplied residue. So 2 pi iota residue other than z naught, because this contour is not containing z naught, that's why you have to find the residue at all other points except this z naught. So these sum of all these 4 terms will be equal to this. So just forget this, I will tell you what is this thing. So here delta is tending to 0 and r tending to infinity. Now you need to find the value of this one, because this closed contour, this C2 can be written as equal to 0. This can be made 0, and we know how to make this 0, because zfz equal to, means you know the conditions for exponential type. You will use z tends to infinity, fz will be equal to 0, and for the simple functions you will use zfz, z tends to infinity should be 0. So you can make this C2 0 there using the Jordan's lemma condition. But we need to find this integral to solve this. So this we call I over. So let's see what is the value of this integral. So see, this is the fz of simple pole. So you can write this fz in this form. A naught plus something is, it will go on, and it is a simple pole, so you will have 1 upon z only up to 1 upon z, and more terms will not be there, only this, means you will have this 1 upon z minus z naught a minus, this is your residue. Okay, so when there is simple pole only, then you can write any fz in this form. So we need to find this I over. So let z minus z naught equal to, means this is making a small circle, so you can write this equation as z minus, here if it is z naught, then z minus z naught should be equal to what? Delta exponential I theta. So this delta is nothing but this distance. So delta exponential I theta, it can be written in this form. Now from here dz will be I delta exponential I theta d theta. Now this I over, we denoted by IO, is nothing but this curve is in this form, so it is going from pi to 0. So limit is pi to 0 for theta. So pi to 0, and fz dz we have to put. So dz equal to this I delta exponential I theta d theta, and fz is this. So I have written this form. Now see, just multiply this delta exponential I theta inside this function. So you will get this will cancel out. So you will get only a minus 1 inside, plus this a naught, then delta exponential I theta and other terms. So when you put delta equal to 0, because delta is tending to 0, so all terms inside this function will be 0 except this a minus 1. So and this d theta. So whatever it will be remaining is d theta integral will give you theta, and theta is going from pi to 0, so it will give you minus pi. So this value of this integral will be minus I pi a minus 1. So this is your I over. So the value of I over is minus iota pi and a minus 1. So this is nothing but residue, residue of fz at z equal to z0. So this is your residue at, means for the fz, whatever the residue at z equal to z0 will be written here. So I over is nothing but this. So in place of I over we will write minus I by a minus 1. So a minus 1 we can find from here, and we will substitute it here. Then we can find the value of this. Means we are not using this point, and we are taking this limit minus r to minus delta and delta to r. So for these axes, this function is completely analytic. So we will call the value of f for these ranges the principal value. Okay. So this minus r to minus delta and delta to r, we call this principal value of fx dx. We are omitting the value of this fx at x0 or z0 because at that point this is singular. So we'll call this one as p fx dx. So in place of this one and this one, we can write this thing p fx dx, and in place of I over we will write this minus I by a minus 1, and this 4 term will be 0. So that's how we will solve this integral, this kind of integral. So let's take one example. Integral is 0 to infinity sin x by x dx. So first, this function is even function, so you can write it in the form of minus infinity to infinity 1 upon 2. Okay, so first what you will do, I told you whenever you will get sin x type something in the function, you will write fz as exponential iz, and in place of x you will write z. So in the last we will compare the things to calculate this integral. So fz is this. Now see, this is 1 upon z is fz, and z tends to infinity. So z means fz equal to 0 for z tending to infinity. So this is Jordan-Lemma condition. It is satisfying Jordan-Lemma condition. So that's why this over integral will be 0. So we can write fz dz as equal to this principal value, means this function is non-analytic or singular at x equal to 0. So on the x-axis for x equal to 0 we are not having an analytic function, so we will remove that point and take the all other values. So and all other values, the integral will be p, principal value. Now this is I over, and this third term will be 0. So that's how you can see this, means this integral is resolved to this thing. This will be equal to sum of these two. Now we already know what is I over. I over is minus I by a minus 1. So we need to find the residue first for this fz at z equal to x equal to 0 or z equal to 0. So let's find. So what is the residue? How you find? Residue is nothing but limit z tends to 0 at 0 and z minus 0 fz. So this will z will cancel out, at z equal to 0 it will give you 1. So residue is nothing but 1. Now the value of this I over will be minus I pi, because it is minus I by residue, so residue is 1. So value of this will be minus I pi, and this principal value can be written in this form, exponential ix divided by x dx. Now let's see this function. What is the value of this function? Because we need to equate all this to this. So this integral is closed integral, and it was written that this function fz is analytic except this point. So we will use the Cauchy integral theorem. Okay, and this fz dz will be 0. So this whole term will be 0, and you can see that also that residue there is no residue for this except at this point. So it will be 2 pi iota multiplied 0. So it will again be 0. So you can write it in any form. So sum of this will be equal to 0. Now then this term will be equal to I pi because this sum will be equal to 0. So this p minus infinity exponential ix divided by x dx equal to I pi. Now see, we already find it this. Now you can write this in the form of cos x and sin x, as we already discussed. So it will give you cos x by x plus sin x by x, and you know here it is I pi, so you can compare the terms. So only the imaginary term will be there. So sin x by x minus infinity will be equal to this pi, and this real term will be 0 because there is no real term. Now from here what you need to find is 0 to infinity, but here we find it is minus infinity to infinity. So this can be written in the form of 2 0 to infinity sin x by x dx. So this 0 to infinity sin x dx by will be equal to pi divided by 2. So this will be your value for this integral. So that's how you solve the integral for which this non-analytic point is on the real axis. So definite integral can be solved by this way. So remember this way, this is very important from the exam point of view. There are many questions asked from this topic. So in the next lecture we will see some more questions related to this, then the last topic, that is branch point singularity for the complex analysis. So thank you everyone. That's it for today.